Hi, I'm Ralph Gable with Electronics for the Inquisitive Experimenter YouTube channel. Today I want to show you how to measure the velocity factor of a piece of transmission line like coaxial cable using your vector network analyzer. You know, it used to be that owning a vector network analyzer, or VNA, would require a huge outlay of tens of thousands of dollars. Well, in recent years, that has really changed. A friend of mine recently purchased a VNA through Walmart for under $100. Now, admittedly, they don't have the precision and capabilities of their much more expensive cousins, but for what we're trying to do, that'll be quite adequate. For the what and why of measuring the velocity factor of a transmission line, please refer to my introductory video on this subject. Now, this method is not restricted to just 50 ohm coax. You must know the physical length of the piece of coax or transmission line that you're going to be testing, and you don't want a micro short piece. You don't want a huge long piece like a 500-foot roll either. You want a reasonable length, maybe 8 or 12 foot of the transmission line. Even a 50-foot piece is not excessive. Okay, so how do you measure the velocity factor using a vector network analyzer? Well, measuring the velocity factor of a transmission line with your VNA is in some ways no different than using your antenna analyzer. What makes it different is the precision of finding the exact frequency where the transmission line is electrically 3/4 wavelength long. For this exercise, I'm going to be using my mini VNA Tiny, which is relatively inexpensive 2-port VNA available from Mini Radio Solution. Okay, so here are the steps. Now we're going to answer the question as to the how. What are the steps for going through and determining the velocity factor of your transmission line? Well, this first step is kind of optional. You can choose to just, ram around and scan and try to determine this. But if you'd like some good guidelines as to what is the minimum frequency and what is the maximum frequency to kind of speed things along in your process, you can calculate the highest possible frequency with this formula here, 0.75 times the speed of light in free space, all divided by the transmission line length. Now I have up here the speed of light in free space is equal to 11,802.9 mega inches per second. Now I have this in mega inches per second because I measure my transmission line length in inches and I want the results in megahertz. So it's 11,802.9 mega inches per second. And for the low frequency, it is the speed of light divided by 8 times the transmission line length. And this will give you the absolute bounds. You're going to want to scan from below the F sub low to above the F sub high so that you can clearly see everything. The next thing is to calibrate your VNA for S11, return loss, reflection, whatever your VNA manufacturer decides to call it. And the important part about this is you want to calibrate your VNA as close to the spot where your transmission line is going to be connected to your VNA as possible. The more stuff in between where your VNA is calibrated and the transmission line that you're actually measuring, the more error you're introducing into your measurement. So calibrate it as close to that spot as you can possibly calibrate it. Next, you can connect your feed line directly to your VNA. No special test jigs or anything, whatever it takes to connect it directly on. Set up your VNA to view phase. We're interested in those places where the phase is changing drastically and very quickly. So phase is what we're interested in. And then you scan from below F sub low to above F sub high. You're looking for those spaces, like I said, where it goes from minus 180 degrees to plus 180 degrees very quickly. And the object is to pick the second one. I've drawn a little picture down here. It'll look a lot like this. The phase, see the orange line, it will come down from plus 180, slowly come down until it hits minus 180, and then right at this spot, bang, it goes up to plus 180, and then it will come down slowly until it reaches another point, and bang, up to plus 180. This first one here is the place where the physical length of your piece of transmission line is exactly equal to the electrical length of 1/4 wave at this specific frequency. And the second one is the place where the physical length of your transmission line is exactly equal to the electrical length of 3/4 of a wavelength. And you say, well, why don't we pick the first one? Well, for whatever reason, it turns out that the second one yields more consistent, more accurate results. So why not use it? So you're looking for these things, and what you should see on the screen is something very much like this. You should see the first dip, bang up to 180, the second dip, bang up to 180. This is the one that you're going to choose. So you're going to choose this one, and you're going to zoom in as needed until you can get right into this spot. And what you're looking for, actually, is the frequency at which the phase is exactly equal to 0. Now, on the mini VNA Tiny, you're not going to get that. But what I can do is I can put a marker down here at the minus 180, put a marker up here at the plus 180, and then say, okay, well, the frequency here is this, the frequency here is this, and I'm going to assume that the frequency that is at the 0 point is halfway between those two frequencies, and that's plenty accurate enough for the kind of thing that we're doing. And so once you get that frequency, then you just do the math. Well, now that we have done the measurement and we have that special frequency where the phase equals 0 degrees, we can do the math. Well, the math that's associated with this method is exactly the same as what we used with the antenna analyzer method. And it begins with the speed of light in free space, which is 11802852677 inches per second. I chose inches per second because I like to measure my feed line lengths in terms of inches as opposed to feet or meters or other such things. The first step is to calculate the length of a quarter wave in free space. We do that by taking the speed of light that we have up here and dividing it by 4 times that frequency that we determined in hertz, and we divide that frequency by 3, so it's 4/3 the frequency in hertz divided into the speed of light in free space gives us the length of a quarter wave in free space in inches. Then we can calculate the velocity factor. We've already measured the physical length of our piece of feed line, so we know that, and that's in inches. We now know from this calculation what the length of a quarter wave in free space is, and we do this division. We divide the physical length by the length of a quarter wave in free space, and that gives us the velocity factor. So that velocity factor should be somewhere between 0 and 1. 1 would be perfect, but generally speaking, you're going to see something between, say 0.6 and 0.8. So that's kind of a sanity check. If you don't get something in that realm, it means you might want to go back and recheck what you've done. All right, so now that we've demonstrated what the math is, let's do an actual measurement on a piece of 93 ohm coax that I have, and then we'll see what its velocity factor is. Okay, so here's my transmission line that I'm going to be testing. It's 93 ohms. You notice that mine does not have a nice connector on the end of it. So I'm going to use this wonderful fixture here on my mini VNA Tiny in order to connect my coax directly up to the front end of my VNA. And this is going to require a little bit of a special calibration because I don't have a connector here. We're going to want to calibrate it as far at the end of this mess as we can. So the mini VNA Tiny wants to have an open, a short, and a load just like any VNA would in order to calibrate out that test fixture. So to do the open, I'm just going to leave it open. I'm not going to connect anything to my little clips, and I'm just going to click on Read Open. And there that is. All right. Now, how do we do the short? Introducing my calibrated short. With my calibrated short in place, I then click on Read Short. And now we need to do the load. This is a 50 ohm 0.1% resistor, my standard quote calibrated load. With my standard calibrated load in place, I then click on Read Load. All right. Now if I want to save this calibration into a file for later, I can click on Save. If I click on Update, it just simply updates the current application so that we can make the measurement. And so now we are just about ready to go, except we need to set our start and stop frequencies so that we know when, what frequencies we're going to be scanning between. Being that my piece of coax is 13 feet 11 inches long, I do the calculations as I previously outlined and determine that the high-end frequency needs to be somewhere around 53 megahertz and the low-end frequency somewhere around 8.8 megahertz. I'm going to set up my VNA to sweep from about 5 megahertz to about 60 megahertz to make sure I capture the whole thing. And so now you can see I've connected my coax up to my test jig. And now let's do the scan. Now notice here we have two distinct spots where the phase goes from minus 180 degrees to plus 180 degrees. We're interested in the second of these two. Well, I've zoomed in on that second spot where the phase goes from minus 180 degrees to plus 180 degrees. And I've placed a marker here, and I've placed a marker here. And so now we can see that marker 1 is at minus 180 degrees, is at 37.486805. Marker 2 is at plus 180 degrees, is at 37.488022. The difference is 1217. So what I'm going to do for my frequency is I'm going to take this number here, marker 1, 37.486805, plus half of this number to give me the frequency where we are sitting right here in the middle between the two at 0 degrees. We've completed our measurement and we have our numbers, so it's time to do the math. We determined that at the minus 180 degrees, we had 37.488022. And then at plus 180 degrees, it was a higher number, approximately 1,217 hertz higher. So we put this together, and we're going to assume that our phase is equal to 0 at 37.488305 megahertz. All right, big bunch of numbers. We can probably drop half of those decimal places, but I tend to keep them. So we have our frequency in hertz that we want in here. So let's put our frequency in hertz in there. In hertz, it's 3,748,630.5 hertz. So we take this value in hertz, we multiply it by 4, we divide it by 3, then we take the speed of light in free space and divide it by the resulting number. And the answer that we get is 236.129 inches. So the length of a quarter wave in free space at this frequency is 236.129. Now we know that the physical length of our coax in inches is 167 inches. I measured that. We know that our quarter wave in free space is equal to 236.129 inches. And if we do this calculation, dividing 167 by 236.129, we get 0.7072. So there is the velocity factor of our piece of 93 ohm coax as measured by the VNA. Well, the next video, I'm going to wrap it all up. I'm going to take the measurements that we made with the antenna analyzer, the measurement that we made with the time domain reflectometry, and the measurement that we made here with the vector network analyzer, and kind of wrap it all up. So thanks for watching. Until then, toodaloots.